So, Samuel, we've been talking about reinforcement learning. This chapter jumps from estimating state values to action values. Why is it a big deal?
Well, Alfred, estimating action values, Q functions, is crucial. They show the value of actions in a given state, not just the state itself. It's like knowing how good a particular move is in chess, not just how good a position is.
Right. That makes sense. So, no need for MDPs?
Exactly. Q functions let us assess actions directly, skipping the need for an explicit MDP, which can be complex. This is incredibly useful when a full MDP is hard to define.
Okay. And how does this relate to policy improvement?
We use these Q-value estimates to improve policies, just like in policy iteration. We evaluate, improve, repeat. It's generalized policy iteration, GPI. This method, works for almost any reinforcement learning algorithm, not just simple ones.
That's interesting. So, we're not just finding the best action, we're continually improving how we choose actions. A bit of trial and error, basically?
Precisely. Agents learn optimal policies through interactions with the environment. It's trial and error learning, which works great for real-world problems.
So, we're talking about learning through experience here, not just theoretical models?
Absolutely. Monte Carlo and temporal difference agents. These are now control agents, and these learn by interacting directly with the environment.
So these control agents are about doing, not just thinking?
Exactly. They decouple learning from behavior, a key advantage. Agents can explore, learn, and adapt without needing a predefined model of the environment. They are very adaptable.
Fascinating. So, more practical application, less theoretical?
Absolutely. This is vital for complex real-world problems. Imagine robots learning to navigate, or games like Go, where complex interactions exist. These control agents excel.
So, Samuel, you're saying every reinforcement learning agent has these three key components?
Yep, that's the core idea. They gather experience, learn from it, and improve their strategies.
Gathering experience. Is that always interacting with the real world?
Not necessarily. They can use simulations or even learned models of the environment.
Like if it's too costly or dangerous to interact directly.
Exactly. Imagine training a robot to walk. Simulating the environment is much safer than having a real robot fall over and break.
Okay, so learning from experience. What kind of things are they learning?
They're figuring out how to best act in the environment. It could be learning a policy, a plan of how to act, or a value function, assessing the worth of different actions.
So, a policy is like a decision-making rule?
Precisely. A policy tells the agent, if you're in this state, do this action.
And improving a policy, that's the ultimate goal?
Absolutely. The agent is constantly refining its policy based on the experience it collects. It's a continuous cycle of learning.
How does that improve over time, though?
It's basically feedback loops. The agent tries things, sees the results, and adjusts its strategies to get better results next time.
Interesting. So, it's not just about trial and error, but about learning from trial and error?
Precisely. Learning to recognize patterns and adjust.
That sounds pretty powerful. But could you give us a real-world example?
Sure. Imagine training a game-playing AI. It's learning the optimal strategy by playing countless games, and improving its policy based on wins and losses.
So, a reinforcement learning agent could eventually master complex games?
Potentially, yes. The more data it has, the better it can perform.
And those three components, gathering, learning, and improving, are crucial for all kinds of RL?
Yeah, that fundamental structure. Whether it's playing games, controlling robots, or even optimizing supply chains.
So, Samuel, you mentioned a key difference between reinforcement learning and, say, supervised learning?
Yeah, absolutely. In supervised learning, you're given a data set. The learning process is pretty straightforward, right?
Right, you're just mapping inputs to outputs.
Exactly. But in RL, agents have to actively explore their environment.
That's interesting. So, the agent has to figure out how to gather its own data?
Exactly. It's a separate challenge from learning from that data. Think of it like this. One agent might be a fantastic data collector, but terrible at learning from it.
Like a student who takes great notes but struggles with test questions?
Precisely. Or someone who understands the material well, but isn't great at organizing their notes. It's about different skills.
So, you're saying there's gathering, learning, and then improving different stages?
Exactly. The gathering stage is important because choosing the right data points is crucial.
So, how does an RL agent choose its data, especially since it's not explicitly told which data points are good?
That's the beauty and also the challenge. It's often about trial and error.
Trial and error. Sounds a bit like a child learning to ride a bike. But how does the agent measure improvement?
Rewards. The agent receives feedback, rewards, based on its actions. Good actions get positive feedback, and poor actions, negative.
So the whole process is driven by rewards?
The agent tries to maximize the cumulative reward over time. It learns which actions lead to greater rewards.
Makes sense. But what about planning methods like dynamic programming? Why aren't they considered RL?
Because they don't interact with the environment. They have a model of the environment, like a map, provided beforehand. So, no learning required.
So, you're saying RL truly focuses on learning through interaction?
Definitely. It's interactive learning, learning by doing. Unlike non-interactive learning, where you learn from pre-existing data.
Right, like learning from examples or historical data.
Exactly. In interactive learning, the agent controls its own experience collection. It has to find the samples needed to maximize learning. A constant balancing act.
So, Samuel, generalized policy iteration. Sounds pretty broad. Break it down for us.
Yeah, it's a core idea. Think of it like a feedback loop. Policy evaluation, then improvement. You keep iterating until you find the best possible policy.
Like continuously refining a strategy?
Exactly. You start with some policy, evaluate its effectiveness, then tweak the policy. Rinse and repeat.
And this applies to value iteration too?
Absolutely. Value iteration uses a slightly different evaluation step, but the overall process is the same. Instead of a full evaluation in each loop, it's a quicker estimation. Still leads to optimal results.
So, why this partial evaluation? Why not just fully evaluate?
Well, sometimes full evaluation is impractical. Imagine a really complex environment. Calculating the exact value function is very difficult, especially in real time, even impossible.
Got it. So, the trade-off is speed for perfect evaluation. That makes sense.
Right. There's also the exploration versus exploitation idea. Full evaluation typically means exploiting what we know. Partial evaluation requires exploring, trying different choices, which helps you gather more knowledge.
Interesting. In this exploration, how does that work practically?
The exploration, in some cases, means not immediately choosing the most promising action, leaving some room for random decisions to find better paths. We see that in various exploration techniques.
Wait, this exploration part sounds similar to how humans learn.
Totally. We learn by experimenting, by taking different actions and observing the results. Value iteration reflects this concept.
So, real-world applications, these feedback loops, how do they shine?
They're used extensively, in robotics. Training robots to navigate and interact with the world. You train an agent to do something. The feedback tells you what worked, what didn't.
And if the policy evaluation gives biased feedback, is that a problem?
Absolutely. It's important to be aware of potential biases. Your agent's actions in the environment must be scrutinized. It's crucial to gather and understand diverse perspectives.
Thanks, Samuel. This is super illuminating. Clearly, understanding GPI lets us understand many RL algorithms better. So, Samuel, we're diving into the control problem now. How does this differ from the prediction problem we discussed last time?
Right. Prediction, is about evaluating policies. Figuring out how good a policy is. Control, on the other hand, is about optimizing those policies. It's like, you have a plan, but it's not the best plan. Control finds the best plan.
So, you're saying control's about finding the absolute best possible policy?
Well, best in terms of the given environment, and the reward structure. That's key, you know. It uses the value function to do this.
So, policy improvement plays a crucial role. Can you unpack that?
Yeah, policy improvement takes an existing policy and makes it better. It's like you're tweaking the plan to be more successful. It looks for ways to make actions greedier in terms of the value they produce.
Greedio? Can you give me a real-world example?
Sure. Imagine you're training a robot to navigate a maze. A simple policy might be, always move right. But this is not always the best. Policy improvement tweaks that policy, learning to evaluate if moving left is better in certain parts of the maze based on its expected reward. It's all about making informed adjustments to the policy based on value function information.
Okay, I see. So, this policy improvement, does it on its own solve the control problem?
No, not on its own. It needs policy evaluation. You need to see how well this new policy performs, so you improve the policy, evaluate it, and then repeat, iteratively getting a better and better plan over time.
So, the Generalized Policy Iteration, GPI, pattern. What's the deal with that?
GPI is a framework. It just says, repeatedly evaluate, then improve and repeat. It's a process that helps find the optimal policies. Think of it as a feedback loop in your plan. You improve, you check how good it is, then you improve it again.
That makes sense. In the slippery walk 7 environment? Why is it important here?
It's a great example because it's stochastic. This environment isn't just random walking. Actions have consequences. And this is important. It really shows how an agent can learn to improve policies even when the consequences aren't guaranteed. The agent has to figure out what to do in order to maximize its chances of reward by choosing actions.
So, the agent doesn't know the precise probabilities?
Exactly. It only sees the effects of its actions. The environment's a bit mysterious, and that is exactly what real-world reinforcement learning scenarios are often like.
Clever. So, it's a test of our RL agent's ability to adapt and learn optimal policies in an uncertain world. Okay, Samuel, we're diving into Monte Carlo control. So, this is about improving policies after each episode. How does it differ from, say, policy iteration?
Yeah, policy iteration uses the entire model. Monte Carlo control, though, is model-free. We're learning by interacting with the environment directly, not by knowing all the transition probabilities.
That makes sense. But why estimate action values, QS, instead of state values versus?
Crucially, the V function on its own doesn't tell you the best action. You need the Q function to make greedy choices. Imagine, if you only know the value of being in a certain state, how do you know which action to take to get there?
Ah, I see. So, it's about choosing the best next step, not just the value of the next state. That's a critical distinction. What about exploration?
Exactly. If we just use the greedy policy, we might miss out on better actions. That's why we use epsilon greedy. It balances exploration with exploitation.
So, you're using a decaying epsilon?
That's right. We start with more exploration, and gradually decrease it as we learn more. The decay schedule ensures exploration doesn't vanish too quickly, allowing us to discover potentially better actions.
And the first visit Monte Carlo prediction?
That's a clever trick. We only update the Q value for a state-action pair the first time we visit it during an episode. This avoids overestimating values, which could lead to problems.
So, the algorithm alternates between single steps of Monte Carlo prediction and policy improvement. It's a simpler, more practical process.
Precisely. It's model-free reinforcement learning. No need to build a model of the environment. Just interact and learn. We're learning from the samples we gather, improving the policy with each episode.
Makes sense. So, what about the code snippets you have? Tell me about the decay schedule function.
It calculates a decaying schedule for learning rates, alpha, and exploration rates, epsilon. You input initial and minimum values, the rate of decay, and the maximum number of steps. It outputs an array of decaying values.
What about the generate_trajectory function?
This function simulates an episode. It takes the action selection strategy, and it rolls out an episode in the environment. It returns a number py array containing state, action, reward, next_state, done tuples from each time step.
And the MC_control function?
This is where the magic happens. It runs many episodes. For each, it generates a trajectory. Then, using the decaying learning rate, it updates the Q values for the visited state action pairs. Critically, it uses the first visit method to avoid overestimating. This then updates the policy, gradually improving over time. That's how the whole process works.
So, SARSA, this new algorithm, it sounds like a smarter way to learn, right? How does it improve on Monte Carlo methods?
Yeah, absolutely. Monte Carlo methods are, well, a bit passive. They wait until the end of an episode to update, like taking a test and getting a score only after the whole thing is over. SARSA, on the other hand, learns incrementally.
So it's like learning a new skill, adjusting after every practice session instead of only at the end of a class?
Exactly. It uses temporal difference learning. This means it doesn't need to wait for the entire episode. It can make updates after every step, using estimates of future rewards. It's a much more responsive, adaptive approach.
And this whole Q function, what's the deal with that?
The Q function estimates the value of taking a particular action in a specific state. It's like a guide, telling us how good a move might be. SARSA learns this Q function.
Okay, so how does the code actually do this? I see this select_action function. Can you break down what that's about?
Well, it uses an epsilon-greedy strategy. This means it sometimes takes a random action, the exploration part. This helps the agent discover new and potentially better actions. Other times, it takes the best action according to the Q function, exploitation, maximizing expected rewards.
So, the randomness balances exploration with exploitation?
Precisely. The epsilon value controls how often the agent chooses a random action. Over time, this value often gets lower as the agent learns, so the randomness gradually fades.
The decay schedule function, what does that do?
It helps control the learning rate. It defines how the learning rate changes over time. At the start, you want a larger learning rate, and as the agent gains experience, you want to gradually decrease it. This function does that.
How are we updating the Q function?
Well, it compares the actual reward it received with the expected future rewards, estimated by the Q function. This difference is the temporal difference, TD error. It adjusts the Q function to close this gap.
So, this is more practical for real-world problems?
Definitely. In many real-world scenarios, waiting for a whole episode before updating is a huge disadvantage. Imagine controlling a robot. If we waited for a complete sequence of actions before tweaking the policy, the robot might have already caused damage. SARSA, by reacting much faster, is more suitable for real-time learning.
And what about batch learning? Is it still useful?
Yes, definitely. Batch learning has its place, especially when you have a lot of data collected ahead of time. It's very effective when you're training with a large dataset, even if it's offline.
So, Q-learning? Huh? It sounds radical. This model-free thing, agents acting randomly and still finding the best path. How's that even possible?
Well, it's all about decoupling the learning process from the agent's actions. Think of it like this. Instead of the agent needing to follow a specific strategy, it can explore various options.
Explore? Like just stumble around?
Exactly. It uses a concept called bootstrapping. The agent estimates the value of actions based on those random actions and then adjusts its choices accordingly. It's looking at future rewards based on current estimates, and it works really well.
So, the agent's learning from its mistakes, not just from rewards?
Precisely. And the crucial part is that the agent isn't tied to one specific policy. It's trying different things. It's figuring out the best policy through trial and error, kind of like how a child learns to ride a bike, trying different techniques, falling down, and eventually getting it right.
But how do you evaluate the best policy if the agent isn't following one specific set of instructions?
That's the key. We're not calculating the value of actions based on a particular policy, but on the expected value of each action. The agent learns how good each action is, regardless of the current policy, and uses that information to gradually improve.
So, it's like it has a predicted outcome for each action, and then adjusts its choices based on those predictions?
Yes, that's the core of the bootstrapping process. It's learning the optimal value function, which tells you the long-term value of each state. Crucially, this optimal value function then helps decide the optimal policy.
That's mind-blowing. It's learning from the possibility space, essentially.
Exactly. It's not limited by a predefined set of actions. It's exploring the whole potential decision tree, and it's still figuring out the best approach. It can adapt to any changes.
Is there a downside? Like, how long does it take to learn?
Yeah, it can be slower to converge than policy-based methods. You can imagine all the possible explorations and calculations. Finding the best strategy in every situation is a complex process. But often, the benefits of not being tied to a set path outweigh the slightly increased computation time.
Fascinating. So, Q-learning allows agents to be a bit more experimental in their search for optimal strategies. Makes sense. So, Samuel, you've been talking about Q-learning and SARSA. What's the core difference?
Okay, Alfred. The key difference is how they learn. SARSA learns on policy. That means it learns about the very policy it's using to interact with the environment.
Like learning a new skill by practicing it directly?
Exactly. Think of it like practicing piano. You're learning directly from your own mistakes, improving the very way you play.
And Q-learning?
Q-learning is off-policy. It's like learning from others' experiences, or maybe even from observing how others play the piano, without necessarily playing yourself.
So, it's learning a different policy?
Yes, it learns about a separate policy from the one it uses to interact with the world. Imagine watching a master pianist, analyzing their technique without playing yourself.
How does that affect how they learn? Makes sense intuitively, but what about practically?
On-policy methods are generally more stable. You're learning directly from your actions, so it's easier to track progress. Off-policy can be faster because you can learn from a broader range of experiences, but also more unpredictable.
Like trying a new recipe based on someone else's cookbook versus your own tasting notes?
Precisely. It's about the balance between stability and speed, and the risks involved.
So, in these algorithms, is there a way to compare how well they perform in different situations?
Absolutely. The key is the update equations. These equations tell you how the algorithms adjust their estimates of the value of each action in each situation. SARSA uses the action it actually took, while Q-learning uses the best possible next action.
That's a crucial difference. So, Q-learning's target is always the optimal one, even if it doesn't choose it?
Exactly. It aims for the highest possible reward.
And what about the code you showed? What does it demonstrate?
The code provides the implementation in Python. You see the epsilon greedy strategy in action. You also see how to update Q values over time and how the learning rate decays.
What are epsilon and alpha?
Epsilon is the probability of making a random action, which helps avoid getting stuck in local optima. Alpha is the learning rate. This helps you update your Q values, not too much or not too little. Both decay over time so the algorithm learns from previous information but also keeps exploring.
Can you elaborate on the idea of greedy in the limit with infinite exploration?
It's a fundamental concept in reinforcement learning. GLI ensures that in the theoretical limit, the algorithm will always select the best possible action, but to do so, it must explore all possible choices to guarantee it.
But in real-world applications, how can one truly ensure infinite exploration?
In practice, you can't guarantee infinite exploration. The epsilon greedy strategy is one commonly used way to ensure exploration, gradually decreasing the chance of random actions.
So, practical implications? Where would you use these techniques?
In robotics, game-playing, resource management, any scenario where an agent needs to learn how to act optimally. Like training a robot to navigate a maze, or a self-driving car to manage traffic.
Excellent. Thanks for clarifying those differences. Hey Samuel, we're diving into double Q-learning today. Sounds complex. What's the core issue Q-learning faces?
Q-learning, often overestimates the value function. It takes the maximum estimate of the next state's action values, but that's just an estimate, not the actual maximum.
So, it's using estimates of a maximum to find an estimate of a maximum. That's a bit of a circular problem. Why is that bad?
Yeah, it's more than just inaccurate. These estimates used in TD targets are often biased. Using a maximum of biased estimates leads to a problem called maximization bias.
Maximization bias. Can you give an example?
Sure. Imagine all action values are 0. But our estimates are biased, some positive, some negative. Like 0.11, 0.65, minus 0.44, minus 0.26. The real maximum is 0, but the maximum of the estimates is 0.65.
So, we're getting a misleadingly high value. Why is that a problem?
It compounds errors. We keep picking those high biased values, even though they have the largest error. It's like someone with a positive bias. They're blinded by the shiny stuff, even if it's not great. This mistake keeps repeating.
Makes sense. So, how does double Q-learning tackle this?
It uses two Q functions, Q1 and Q2. Imagine them like cross-validation. One Q function estimates validate the other.
So, it's like having a backup opinion? How does that work in practice?
We use one Q function to pick an action, but use the other to estimate the value. That reduces the chance of always having a positive bias error. To select an action, we average or some Q1 and Q2 for that state.
How does the code for that look in Python terms? Can you give the gist of it?
See, in the code we pick an action using one Q function, but get the estimate from the other. It flips a coin to determine which Q function to update. Crucially, it uses the other Q function to calculate the TD target.
Right. So, we're using different estimates for different parts of the calculation. This seems much more stable. Are there any downsides?
Yeah, the training slows a bit, as we're splitting the experience between functions. But it leads to much better long-term performance and more stable estimates. It's a trade-off.
Makes sense, thanks Samuel. This is really helpful. So, double Q-learning is less prone to these overestimation issues than regular Q-learning. Is there anything else critical to consider when employing this approach?
Yes, using decaying learning rates for the alpha parameter is key for convergence. A constant alpha often prevents the algorithm from settling on the optimal values. Epsilon decaying is also good. Epsilon often stays constant and gives great results in practice, but decaying it to 0 aids in convergence.
Great insight. So, in short, double Q-learning addresses maximization bias by splitting estimations between two Q functions, improving stability and reducing overestimation issues compared to standard Q-learning, at the cost of a slower training process. So, Samuel, this chapter's all about putting reinforcement learning into action, right?
Exactly. We're moving from just predicting what will happen to actually controlling outcomes.
That's a big leap. Can you explain the difference between prediction and control?
Sure. Prediction, like in the last chapter, is about evaluating policies. It's like saying, if I do this, what's the expected outcome? Control, on the other hand, is about finding the best policy, the one that maximizes those outcomes.
So, control is more proactive?
Precisely. We're not just assessing, we're optimizing. And it's not as straightforward as you might think.
What's the catch?
Well, the prediction methods from before don't directly translate. We need new tools for finding the best policies.
Why?
We need methods that can learn action values from samples, plus ways to explore different actions to find the best ones. Just improving policies isn't enough. It's like trying to find the best path through a maze. You need to evaluate different paths while trying them.
So, what's this generalized policy iteration, GPI?
GPI is the key pattern. It combines policy evaluation, figuring out the value of a given policy, with policy improvement, finding a better policy. They loop. Evaluation refines our understanding, improvement changes the policy.
Like a feedback loop?
Exactly. It's an iterative process to get better and better.
So, better policies until
we reach optimal policies. The ones that give the best possible outcomes. This works in simple, discrete environments.
What about more complex, real-world scenarios?
Yeah, there are more sophisticated methods for those cases. We'll explore those next chapter. More effective algorithms exist for very challenging tasks that can learn optimal policies faster.
So these new control methods need fewer trials or experiences.
Exactly. You're right. They use available data more efficiently to find optimal policies.
Fascinating. So, we're essentially learning from past experiences and constantly refining our approach.
That's the core concept of reinforcement learning. And this chapter is where you understand the core structure to solve the control problem.